Hi, my name is Michael Wojcik, and I will be presenting my project for the pattern recognition class at University of Florida, spring semester 2017. My project is on a handwritten digit recognition system using parallel neural networks. The project plan was to develop a simple, highly parallel neural network scheme to demonstrate how an FPGA could be beneficial to the implementation of neural networks. So I chose handwritten digit recognition as the uh, classification object of my neural network. I will be using the MNIST 60,000 training samples and 10,000 test samples for my neural network. The implementation is as follows. The encoding training phase is unsupervised. There will be a neural network for each digit, and these will be encoded, trained in parallel. So first there's a pre-process phase, which is going to reduce the bit width of each digit to 1 bit. And then it's going to encode the digit based on a principal component analysis, which I'll get into later. Then after the training phase, there will be a testing phase, and the test samples will be pre-processed the same way to a 1-bit width. And then the decode will use the encoded mean and variances principal component analysis determined from the training phase, and the classification will be based on a soft decision methodology. So the encoder, it's going to look for 16 partitions of the digit. It's going to do so by first finding the center of mass of the digit. Relative to that center of mass, it's going to implement a grid, finding the center of mass of the 4 quadrants. It's going to repeat that process for each quadrant, and it's going to break up each quadrant into 4 partitions. So 4 times 4 is 16 partitions total for the digit, and the center of mass in each of those partitions is going to be used to develop a mean and variance for each partition that has a center of mass. There is also going to be a mean and variance representing the total number of partitions with a center of mass for each digit, as well as a mean and variance per quadrant for the number of partitions without a center of mass. The decoder is going to take these mean and variances and determine a probability for each partition based on the testing sample center of masses determined. The classification will then be based on a soft decision where the decoding process is going to present a probability per partition. It's going to be summed up, and the digit with the greatest probability will win. The decoding process will have each of these digits compared in parallel. So here is an image of the encoder. On the left side, you'll see that the input samples will be fed in, and the first oval shape is talking about the quad encoding, where it's looking for the number of partitions without a center of mass. The next is going to be the total number of partitions with center of mass for that digit, and that's the second oval shape. And then each individual partition is going to have a center of mass, and there's going to be a mean and variance describing the location of that center of mass for each digit. Each digit will be encoded in parallel, and the output is the output encoding for each digit. So the dimensions are going to go from a 784 dimensions of a 28 by 28 pixel resolution image to 74 dimensions as the 32 means, variances, the 4 means and variances, and the 1 mean and variance from the partitions, quadrant partition invalid probabilities, and the total partitions valid are summed up. So onto the decoder. The decoder is going to first determine the 16 partition centers of mass, the X and Y pairs. It's going to plug this into the PDF determined by the encoder. So it's going to plug these values into a Gaussian normal distribution equation using the encoded mean and variances to determine a probability. This probability is then governed by the probabilities of the valid partitions and the quad invalid partition probabilities. The valid partition probability and the quad partition invalid probability are summed together and then multiplied by the 16 partitions probabilities to govern them, and the output probability is the sum of all those 16 partitions, and then the classifier will look at each of those values and determine that the digit to be chosen is the one with the greatest value. So here's an image of the decoder. It's going to take the input sample on the left. It's going to look for the quad number of partitions that do not have a center of mass. It's going to look for the number of partitions total that have a center of mass. Then it's going to look for the center of mass for each partition. It's going to sum the probability of valid partitions with the probability of invalid quad partitions. And then it's going to multiply that by each of the partitions relevant to that quadrant. And it's going to govern each of the probabilities of those partitions with this governing criteria. And it's going to output a probability for each digit. The classifier is then going to take these probabilities and determine which digit needs to be chosen. So here are the results. This was a disappointing outcome at the first glance, but I was able to improve the results by about 3%. So the results were the initial design produced a result of 26.67% accuracy. I was able to get it to a 29.45% accuracy with the governing of the quad invalid partitions and the total partition valid governing rule. The theory behind that was to look for moments of digits where they didn't have a center of mass, like some digits have negative space, holes in the center, or they just don't have, the symbol doesn't extend to the left as much as others. And then also I was looking for images that were smaller or larger with this governing rule as well. I also attempted to feed the results forward for the incorrect digits to see if I could better train the encoding, but I found that that actually reduced the accuracy by about 6%. So the reason for these poor results can be kind of observed in this slide. If you look at the partitions and compare the two, you'll see that a lot of the partitions' mean and variances of the digit 3 and the digit 8 are similar. And there's a possibility that a digit 3 center of mass might produce a greater probability in the digit 8s from the digit 8's encoding values. There's just a few that stand out to be, kind of difference, like the variance for, let's say, 15 or partition 15 or partition 13. But the means, yet again, are very close for those partitions. So there's only a handful of partitions where there might be enough of a difference to create a greater probability in one than the other. But for several digits, this principal component analysis was a poor choice of distinguishing between digits because for many of them, they had similar centers of masses. So for digits 1 and 2, 3 and 5, 6 and 9, 3 and 8, 4 and 9, 7 and 1, they were very similar. For instance, the 4 and the 9, both those intuitively look very similar. So this became the problem with this low accuracy. That's the reason why this occurred. So the second part of this project was to demonstrate how a neural network could be, its efficiency could be increased by use of an FPGA. Neural networks are inherently parallel. FPGA hardware is inherently parallel. So many neural networks can be improved in terms of the time it takes to get results if implemented on an FPGA. So this slide presents the encoder on the left and the decoder on the right, and the big O analysis if implemented with a serial implementation of instructions versus parallel implementation of instructions. So for the encoder, if implemented sequentially, the instructions are implemented sequentially, it comes to a big O n to the power of 3. But if it was able to be implemented in parallel, it would drop to a big O n. For the decoder, if it was a synchronous or chronological implementation of instructions, it's at a big O n to the power of 2, whereas in parallel, it would go to an O n as well. And it would be representing the number of samples fed into the encoder or decoder. So as demonstrated with this neural network, an FPGA could greatly reduce the time it takes to come to a result in the training phase or the testing phase. So the results regarding the efficiency increase when implemented in parallel were pretty good. When implemented in parallel, the encoding phase sped up 15 times more in parallel, and the decoding phase was 267 times faster in parallel. Now, I was unable to fully implement this in parallel because I was not able to have child processes send processes in parallel. And so the design, as these results are demonstrating, has the encoding phase encoding each digit in parallel, but everything in that encoding phase is going to be sequential instructions. And then in the decoding phase, each test digit, is going to be compared against each of the digits encoding in parallel. But the partitions and the other processes internal to that will unfortunately were sequential as well. If implemented on an FPGA, this would be very possible, and would expect even larger speed ups. So I'm going to end this presentation with a video on the demonstrating the neural network. You're going to see the results being generated at the end. It's going to show you the number of correct, incorrect. It's going to move pretty fast because it's implemented in parallel, and at the end it's going to present. It's going to be showing the amount of time it takes per test sample that it's classifying. So thank you for listening to my presentation, and go to the next YouTube video for the demonstration.